All right, we're almost at the end of our notes. In this video, we're going to look at our geometric sequences on 8.3. And we remember from algebra that a geometric sequence is a sequence where consecutive terms have a common ratio. Another way of thinking about that is you'll notice a multiplication or division pattern in the sequence. So when we're talking about the common ratio, if you pick any term and divide it by its previous term, you will get that common ratio. So you can see it's been done here. They all divide to 2 to 1, a 2 to 1 ratio. So if we look at these examples, we're going to decide which are geometric. You might want to pause the video, try it for yourself, and then check it after. All right, in example 1, I notice in example 1 that I see a multiplication pattern there. So when I see that times 3 times 3 times 3, I know it's geometric. I could also check by dividing and say, all right, well, 27 over 9 is equal to 9 over 3 is equal to 3 over 1. All right, in B, I see that we're adding, there's an addition pattern, but there's not a common ratio. So this one is not geometric. In fact, that one is arithmetic. Part C, this one's also geometric. So my ratio, is going to be a 1/3 or 1:3 ratio. So I might notice a multiplication pattern. 2 times 1/3 is 2/3, times 1/3 is 2/9, times 1/3 is 2/27. You might think of that as a division pattern, dividing by 3. But if you, let's say I did 2 over 27 divided by 2/9, well, that's the same as multiplying by 9/2. I would end up getting the ratio of 9 to 27, which is equal to 3 to 1. So all of these, or sorry, no, it's not, sorry, equal 1 to 3. That helps. All of these have a multiplier of 1/3. And then lastly, letter D, you might notice that there's alternating signs here. It goes positive, negative, positive, negative. That can happen in a geometric sequence if your common ratio is negative. So if we check it out, negative 8 over 4 reduces to negative 2. Positive 4 over negative 2 reduces to negative 2. And then negative 2 over 1, of course, reduces to negative 2. So that one actually is geometric also. The common ratio is negative 2 to 1. Geometric sequences, there is a formula that you can use to write the explicit formula. And on the first page of your notes, I kind of took you through the Algebra 1 method where we would compare this to like y equals b times g to the power of x. And for this method, the benefit to this is you don't have to find the 0th term, which would be kind of the equivalent of our y-intercept if we're thinking of an exponential function. So in this sequence, you can actually just use the first term. So you might find that you like this better as far as finding the sequence, the explicit formula. We're going to talk about this partial sum in just a moment, but just like with an arithmetic sequence, there's a formula for adding up a certain number of terms in the sequence. And our last example will do a formula like that. All right, so in example 2, find the nth term formula for each sequence. So the nth term formula is the same as saying the explicit formula. We don't want the recursive. All right, so in A, I'm going to look up here at what's in this box and kind of use this way of structuring my equation. It says that for any term, so A sub n, I can write it, so I have my first term, so our first term is 1 here, then times the common ratio, so that's what the r is. So my common ratio here, I could do, oops, sorry, hit the camera, negative 27 divided by 9 and get negative 3. So my common ratio is negative 3. And then all that to the power of n minus 1. So this is nice. It doesn't require you to work back and find the 0th term, but instead of being to the power of n, it's the power of n minus 1. All right, in letter B, or example B, example 2B, I guess, we're given the recursive formula, and we are asked to write the explicit. And so all we really need that we're not given is that common ratio, because we have our first term, and then this is our recursive. So if you can just think about how this reads, this basically says to get to the next term, you're going to multiply 2/3 by the term before it. So if my first term is 4, to get to my second term, I'm going to multiply 2/3 by a sub 2 minus 1, which is just my first term. 2/3 times 4. So I would get like 8/3 there. So if you think about it, if you keep this pattern up, then to get to a sub 3, I'm going to multiply this term by 2/3. Well, we have our common ratio. We're multiplying by 2/3. Or I could just look at these first two numbers in the sequence, 4 and then 8/3. And if you do 8/3 divided by 4, that's the same as 8/3 times 1/4. You get 8/12, which is the same as 2/3. So anyways, we're given the common ratio there. We just have to pick it out of that recursive formula. So now we could write our sequence. A sub n is, we're going to use the first term, so 4 times the common ratio, so times 2/3, to the power of n minus 1. All right, excellent. Example 3. Now we are asked to find the 20th term of each geometric sequence. In order to do this, what we really need is the explicit formula. We need to write an explicit formula. I don't want to be multiplying numbers by a ratio 20 times. So we can actually work this backwards to figure out the first term if we know a term. So if I know that a sub n is equal to the first term times the ratio, the common ratio, to the power of n minus 1, and then I know my fourth term, here's what we can do. We could say a sub 4 is equal to a sub 1, I'm going to use r again, so times my ratio, to the n minus 1 power. So this would be to the 4 minus 1 power. So now I'm going to substitute 9 for a sub 4. So 9 is equal to my first term, a sub 1, times r, which is 1.2, to the third power, because it's 4 minus 1. All right, so now I actually have to do that. 1.2 to the third power is like 1.728. So I get 9 equals a1 times 1.728. Then it's just a one-step equation. I can divide both sides by 1.728. Those cancel. 9 divided by 1.728 is 5.208. So that's my first term. Okay, so if that's my first term, I can now write the explicit formula that a sub n is equal to my first term times my common ratio to the n minus 1 power. So now to find the 20th term, I would just do a sub 20, equals 5.208 times 1.2 to the 19th power, 20 minus 1. And if I did that correctly, we should get approximately 166.385 for that 20th term. Whew, it's a lot of work. All right. Letter B, example 3B. Same kind of idea here. We're not given the common ratio, but we're given the first two terms. To find the 20th, again, we really want to get to that explicit formula. So this time we're going to pick the common ratio out from the sequence. So if my sequence goes from 50 to negative 25, I could divide negative 25, the second term, by 50, the first term, and simplify that to the common ratio of negative 1/2. So that's your R value. All right, so now we could set up our explicit formula that a sub n is equal to a sub 1 times our common ratio to the power of n minus 1. So then to find the 20th term, we'll just plug in a 20. So a sub 20 is 50 to the negative 1/2 to the power of 20 minus 1 to the 19th power. And when you plug this in your calculator, you're going to get an answer in scientific notation. And so let me pull out, sorry, I'm not prepared. I don't have my calculator with me. I do, it was just not handy. All right, so let's plug this in. I'm going to do 50 times negative, I'm going to just do 0.5, same as a half, to the power of 19. And I get, if I were to just write down what I get that a sub 20, I'm going to write approximately, and then I'm going to see negative 9.537, and then some more numbers, and then the letter E, and then negative 5. And what that is the same as saying times 10 to the negative 5th power. So this is scientific notation, and it's telling us to move our decimal over 1, 2, 3, 4, 5 places to the left of that. So really, it's like negative 0.00009537 and so on. So I'm just going to round this and say that a sub 20 is approximately negative 0.0001. So it's a pretty small number.